The analysis of the pink noise filter presented in the previous video may have seemed a little bit cumbersome because it did not rely on any fancy computational tools, only our brains. This sort of approach has a couple of advantages. I have found that sometimes when you do lots of computations with calculators or computers, particularly computers, you get so much information that you really lose sight of the forest for the trees, as the saying goes. You just get too wound up in the details to see the overall picture. The other, and perhaps more important advantage, is that you can rely on this sort of analysis when your computational tools are not available. I frequently resort to this sort of an analysis when I've been mulling over a problem for some time, and I'm in a situation where I do not have access to my computer or my calculator or whatever, such as when I'm riding my bike or lying awake in bed at night or walking on the beach or whatever it happens to be. In fact, the first time I really understood how this pink noise filter works, I did the analysis in my head while driving down the road out in the middle of nowhere. But now let's put this same type of analysis on a little bit more substantial computational footing. Let's actually calculate, plot, and compare the impedances of the three branches of the filter. I used MATLAB to do this, but you could use any sort of tools that you're comfortable with. First, the impedance of the resistor is just constant, so it's going to give us a horizontal line on our graph of impedance versus frequency. Next, the impedance of the 1 nanofarad capacitor is going to constantly decrease as frequency increases. And since this is a 1 over f relationship, if we plot this on a full logarithmic graph, it will give us a straight line with a negative slope. Now note, if these were the only two components in our filter, it would act like a low-pass filter. Note that at low frequencies, below say about 100 Hz, the 330K resistor has a considerably lower impedance than that of the 1 nanofarad capacitor, and so the 1 nanofarad capacitor does not affect the overall impedance much at all, and that overall impedance is almost constant, thus the response of the filter is almost constant. At high frequencies, say above 2,000 or 3,000 Hz, the reverse situation is true. The 330K resistor has an impedance considerably greater than that of the capacitor, and so it does not bring the overall impedance down much at all in that parallel combination. The overall impedance is approximately the impedance of the capacitor. The impedance is constantly dropping, and so your response is constantly dropping. In between, near where the two impedance lines intersect, is your transitional region where it's transitioning from a flat response to a minus 20 dB per decade response. At the point where they cross, where the magnitude of the impedances is equal, that's your corner frequency. If you calculate this out, you get about 482 Hertz for the corner frequency. If you look at the graph, that indeed is where they cross, although you can't read the graph quite that accurately. Finally, let's add that third branch, the one with the 10 nanofarad and the 47K resistor. At sub-audio frequencies below about 20 Hertz, the 330K impedance is considerably less than the 10 nanofarad branch, which in turn is considerably less than the 1 nanofarad impedance, and so the 330K is close to the overall parallel combination. The others drag it down just a tiny little bit, but it's very, very small, and so for sub-audio frequencies, the response is almost flat. For very low audio frequencies, perhaps between about 20 Hz and 100 Hz, the impedance of the 10 nanofarad branch and the 330K are getting fairly close. The impedance of the 1 nanofarad is still considerably larger, but the response is beginning to drop due to the 10 nanofarad branch. For low audio frequencies between about 100 Hz and about 400 Hz, the branch with the 10 nanofarad capacitor and 47K resistor is the smallest. That dominates the overall impedance, and so your response is dropping at roughly 20 decibels per decade. At mid-audio frequencies between about 400 Hz and about 1500 Hz, the impedance of the 10 nanofarad branch is still lower than the others by a considerable margin, although the impedance of the 1 nanofarad capacitor has now dropped below 330K. However, the impedance of the 10 nanofarad capacitor and 47K resistor is now approaching 47K asymptotically. In other words, the impedance of the 10 nanofarad capacitor itself has dropped below about 50K and is heading towards zero, but you've still got that constant 47K. Since this is still the dominant impedance in the parallel combination, the overall impedance is not changing very much because the 10 nanofarad 47K impedance is not changing much, and so your response levels out. For frequencies between about 1500 Hz and maybe about 5000 Hz, the impedance of the 1 nanofarad capacitor and the 10 nanofarad 47K branch are very close to each other, but the impedance of the 1 nanofarad is starting to drop below the impedance of the 10 nanofarad branch, and so your response starts to drop again. And finally, as you go beyond about 5000 Hz or so, the 1 nanofarad branch becomes the smallest of the three impedances by a good margin, so the other two do not affect the overall parallel combination much, and your final response approaches minus 20 dB per decade or minus 6 dB per octave. As inadvertently falsely claimed in the previous video, we will now move on to our sub-audio random noise source.